Hello everyone. In this lesson we're going to start on the notes on intermolecular forces of attraction and polarity. This will be broken up into a few different videos, each one covering slightly different material because it is kind of long. So let's start with polar molecules and which molecules are polar. Now, this all gets back to electronegativity. I'm not going to read this to you, but remember electronegativity, it means an atom's ability to attract electrons to itself. The greater its ability to attract electrons, the closer those electrons will bind to it. Fluorine being the most electronegative atom. If the difference in electronegativity between two bonded atoms is strong enough, then it will form a polar bond. So here's the periodic table that shows electronegativity values, right? There's fluorine. Fluorine, of course, has the greatest electronegativity, and then francium down here is the least. In general, the closer you get to fluorine, the higher the electronegativity. Now, general rule of thumb on this, when electrons are shared unevenly, we have a polar bond. When they're shared evenly, we have a nonpolar bond. And then the shape of the molecule is actually going to be what determines whether or not we have a polar molecule. So to determine if a bond is polar, we just need to know if the difference in electronegativity is greater than 0.5 or less than 0.5. So if it's 0.4 or less, we say the bond is nonpolar. If it's 0.5 or greater, then the bond is polar. Now, this says here to mark all the bonds on a worksheet with as polar, and so worksheet 5.3, I want you to go through on those molecules and mark the bonds. Now I'm going to do a couple here. We have bromine, and bromine is of course nonpolar. There is no difference in electronegativity between two atoms of the same element. So this is a nonpolar bond. There is nothing to mark. However, CF4, carbon tetrafluoride, if we draw that Lewis structure, we've got fluorine, 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 and we have all of the lone pairs. Then the question here is this a polar bond? And the answer is this is 4 polar bonds. Fluorine has an electronegativity of 4, and carbon has an electronegativity of 2.5. which is a difference of 1.5. That's a very polar bond, and so we get what's called an induced dipole. And so in the bond, this is going to end up pulling a slight negative. And so this is the Greek letter delta. It's a lowercase delta, and that's what we use to mark the side that has the higher electronegativity because the electrons are pulled towards it. So each one of these gets a D minus, because each fluorine has the higher electronegativity. Selenium hydride, selenium dihydride, SEH2, that also is polar because selenium has an electronegativity of 2.6 and hydrogen has an electronegativity of 2.1, so that's a difference of 0.5, so it's just barely polar. So we have selenium and our hydrogens. This would be a bent molecule, and these would be pluses. Selenium is actually the more electronegative, right? So you can draw these arrows that show where the pluses are, but we'd have a partial D minus here, and we'd have our partial D plus here, and a partial D plus here. So those are our dipoles. And then NF3, nitrogen has an electronegativity of 3, and fluorine has an electronegativity of 4. So this is, of course, a polar bond. So we've got nitrogen, fluorine, 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 and then our lone pair here. And so this would be a D minus, D minus, D minus, and we would have our bonds actually headed this way, right? That's the direction the electrons are pulled in each one. So determining bond polarity is simply a matter of finding the difference in electronegativity. You can use the electronegativity table for that. And then determining which one is more electronegative. The one that's more electronegative is going to have the electrons pulled towards it as long as the value is 0.5. The difference in the values is 0.5 or greater. And you're only considering a pair of electron or a pair of bonding atoms at a time. You're not considering the whole molecule, at least not yet. Now, molecular polarity is when we actually say, okay, well, let's determine whether or not the molecule is polar. So a polar molecule means the electrons are unevenly distributed. Basically, there's got to be an asymmetry in there. And if there's an asymmetry in there, the electrons can pile up closer to one place, then we'll have a slight negative charge. We will get a polar molecule. Now, nonpolar molecule just means the electrons are evenly distributed across the molecule, so the molecule is neutral. It is possible to have polar bonds and nonpolar molecules. If we have nonpolar bonds, then we have nonpolar molecules. And so the way we get a nonpolar bond, the way we get a polar molecule, a nonpolar molecule with a polar bond, is by looking at the shape. So we're going to start with the Lewis structure. We're going to determine the molecular geometry. We're going to determine if the bonds are polar or nonpolar. We're going to label our partial positives, partial minuses, and if all of the bonds are nonpolar, it's nonpolar. If we have polar bonds, then we use the shape to determine where the negative and positives end up. If they pull against each other, then they might actually cancel out. If they don't, then we'll have a polar molecule. So we're looking for asymmetries. So let's look at those molecules again. So Br2 is still a very nonpolar bond. So there's really nothing to do here. There is no dipole. There is no difference in electronegativity. We don't have to worry about it. However, CF4, so carbon tetrafluoride, we already established that this is polar, and whoops, that's a fluorine, and we've got all our lone pairs hanging out, and what we need to do is determine whether or not the molecule is polar. Well, here's the deal. This is a symmetric shape. This is tetrahedral geometry. Okay. Now remember, in the tetrahedron, it's not only tetrahedral electric group geometry, but it's also a tetrahedral molecule. This thing has these 4 fluorine atoms evenly distributed around it. So while it is true that this bond is trying to pull the electrons this direction, and this one's trying to pull in this direction, and this one's trying to pull in this direction, and this one's trying to pull in this direction, there is no asymmetry here. Every fluorine is equidistant from every other fluorine. Every fluorine is trying to pull electrons, and the net result is this is a nonpolar molecule with polar bonds. Because the polar bonds, yes, the fluorine is trying to pull the electrons towards it, but because then they cancel out, they pull in opposite directions, it's a nonpolar molecule. Selenium hydride, on the other hand, selenium is a group 6 element. It's got 6 valence electrons. Hydrogen makes a single bond. Hydrogen makes a single bond. Now our Lewis structure looks like this. It's 4 electron group geometry, but it's removed. It's got 2 lone pairs, and that makes this bent. Okay. Well, the bent shape, since the dipole moment is this direction, we've got a D minus here and a D minus here and a D plus here and a D plus here. That actually does not pull against each other. We end up with a polar molecule, and our polar molecule actually has the positive charge. This is a lot like how water looks, piled up around the selenium. So we end up H, H, and this side of the molecule has a slight positive, and this side of the molecule has a slight negative. There is our polar molecule. And then finally we have NF3. Now nitrogen trifluoride is a little bit tricky because it is 4 electron group geometry. We have 3 fluorines, and we have 2 electrons, our lone pair there, and then we also have our lone pairs around all of our fluorine atoms. Now this is tetrahedral geometry for the electrons, but it's trigonal pyramidal for the actual molecule, and that's not symmetric. Remember, these electrons actually push the fluorines all closer to each other. So we're actually going to end up with, we've got a partial minus here, a partial minus here, partial minus here, but nothing over here pulling against that partial minus if you want to think about it. And so a trigonal pyramidal is not perfectly symmetric. These fluorines got pushed closer to each other, and so our molecule actually ends up with a slight dipole on it. Over on the fluorine side, we're going to have a slight negative because the fluorine is pulling the electrons closer, and on the lone pair side, we'd actually end up slightly positive because the electrons are getting pulled towards the fluorine atoms.